Welcome to all in the lecture series of functional analysis. Today in our lecture we see the topic linear operators and functionals on finite dimensional spaces. So in the first part we see linear operators on finite dimensional spaces, and in the second part we see functional, that is linear functional on finite dimensional spaces. So we consider in this topic vector spaces which is finite dimensional, and on that vector spaces we see the linear operators. Actually we prove in this topic, we show that linear operators on finite dimensional vector spaces can be represented in terms of matrices. That means linear operator is represented in terms of matrices, but it is true only for the finite dimensional vector spaces, and therefore the matrices become the most important tools for studying the linear operators, because linear operators can be represented in terms of the matrices, and therefore so we start with the finite dimensional vector spaces. Here we consider capital X and capital Y be finite dimensional vector spaces, but here we consider their scalar field is same. Let capital X and capital Y be finite dimensional vector spaces over the same field. And capital T, which is from X to capital Y, be a linear operator. As capital X and capital Y are finite dimensional, that means here dimension of X, here we consider the dimension of X, that is equals to n, and here we consider the dimension of Y, that is equals to r. Capital X is finite dimensional with dimension of X, that is equals to n, which is less than infinity, and dimension of Y, that is equals to r, that is less than infinity. As they are the finite dimensional, therefore the basis for capital X and basis for capital Y is exist, and therefore we choose a basis for capital X as E equals to, we are writing the basis element E1, E2 up to so on En. This is the basis for capital X, and basis for capital Y as capital B, that is equals to B1, B2 up to so on Br. This is the basis for capital Y, and here the basis for capital X is equals to E1, E2 up to so on En, with the vectors arranged in a definite order which we keep fixed. That is very important for us, because here the vectors arranged in a definite order which we keep fixed. That is very important to see the matrices, and therefore here as E is equals to E1, E2 up to so on En, it is the basis for capital X, and therefore for any small x belongs to capital X has a unique representation as x is equals to, here we are writing xi1 E1 plus xi2 E2 up to so on plus xin En. This is the very unique representation for capital X. Now here as t be the mapping from capital X to capital Y, and here we take small x be the element of capital X. That means small x is here. T is applying on capital X, that means T is applying on each element of capital X, and therefore T is applying on this X, and the image, that is Tx, it is now the element of capital Y. And therefore here Therefore, small x has the image y, that is equals to tx. Now here putting the value of x, that is equals to t of, the value of x is xi1 e1, xi2 e2 up to so n plus xn en. That is equals to, in terms of summation, it is equals to t of summation k is running from 1 to n xi k en. This is the value of, not en, this is ek. Xi k ek, this is the value of y. Now here again, as y, that is equals to tx, it is the element of capital Y. Capital Y is also finite dimensional and basis for capital Y is also given as y is the element of capital Y and capital B equals to the set containing the elements B1, B2 up to so n Br is a basis for capital Y. Therefore, this small y has a unique representation. Y equals to, we write down it is equals to eta 1 b1 plus eta 2 b2 up to so n plus eta n br. Eta n br. And eta r br. This is the unique representation for capital Y. That means in terms of summation, we can write down summation j is running from 1 to r eta j bj. We give it the equation number as we are taking the value of x, that is equals to the summation k is running from summation k is running from 1 to n. Here the value of x is xi k ek. We give it the equation number 1. After that we have the equation y, that is equals to tx, and then we get this, it is equals to the summation k is running from 1 to n. The value of tx is summation k is running from 1 to n. This is xi k into tek. We give it the equation number 2, and now this y equals to the summation j is from 1 to r eta j bj. We give it the equation number 3, because here we have to combine all these equations, and that's why I am writing here all these equations. Now again here, as y is the element of capital Y and it is the basis for capital Y, therefore we can write down small y has a unique representation in terms of the basis b1, b2 up to so n br, and we write down y equals to the summation over j is running from 1 to r eta j bj. Now in the same way as e1, e2 up to so n en, e1, e2 up to so n en, it is the basis for capital X. As it is the basis for capital X, that means for each k, ek is the element of capital X, and here t with the mapping from, that is the linear operator, from capital X to capital Y, and therefore for each k, ek belongs to X implies that tek is the element of capital Y, and as tek is the element of capital Y and y has a basis b1, b2 up to so n br, and therefore for each k tek has a unique representation in terms of the basis, and therefore for each k tek it is equals to the summation j is running from 1 to r tau jk bj. Now here I am writing the coefficient of bj is tau jk bj. Now I am writing here tau jk bj because corresponding to this k I am writing here k, and corresponding to this j I am writing here tau jk into bj, because here I am giving the equation number If this is the thrice A, then this equation is thrice B. That means here for each k TEK, that is equals to the summation over j is from 1 to r tau jk bj. This is the thrice B. And tau jk, in that k is corresponding to this k and j is corresponding to this j, and therefore we write down it is as tau jk. Now observe here, we know, as we see here, y it is nothing but the image of x. Y it is nothing but the image of x, and here we calculate the value of y in terms of the basis b, that is the set containing the vectors b1, b2 up to so and br. Also here we have the value of x, because small x is the element of the, that is the vector of the vector space capital X, and capital X is finite dimensional, therefore it has a basis e1, e2 up to so and en, and therefore here now we are putting the value of y, and here we are putting the value of tx from equation thrice A and equation 2. The value of y is, here we get the value of y is summation j is from 1 to r eta j bj. This is the value of y from equation thrice A, and it is equals to, now we are putting the value of tx. The value of tx is summation k is running from 1 to n xi k tek. This is the value of tx. Now here again we are putting the value of tek from this equation thrice B, that is equals to summation over k is from 1 to n xi k. Now the value of tek is, we keep it in bracket, summation j is from 1 to r tau jk bj. That is the value of tek, and therefore this is also written as, it is equals to the summation j is from 1 to r, in summation we write down k is from 1 to n xi k tau jk into bj. This is the summation over j is from 1 to r into this bracket into bj, and it is equals to the summation j is from 1 to r eta j bj. Now in this equality, here in this side we have this bj, and also in this side we have this bj, and this bj for each j, the set b1, b2 up to so and br, this is the basis for capital Y. As it is the basis for capital Y, and capital Y is a vector space, therefore this basis must be linearly independent set of vectors. That means for each j, bj is linearly independent, and as each bj is linearly independent, that means this the set of all the bj's form the linearly independent set of vectors, and therefore the coefficients on each side must be equal, and therefore here we write down, therefore for each j we are getting, here the coefficient of bj is eta j, and here the coefficient of bj is this summation. For each j, eta j, it is equals to summation k is from 1 to n xi k tau jk. That means for each j we are getting the value of eta j in terms of tau jk xi k. Now we give it the equation number 4, and here j is running from 1 to r for all j equals to 1 to up to so and r. Now we write down this equation again. for each j, eta j, it is equals to summation over k xi k into tau jk. This is our equation number 4. Now in this equation, as this equation is true for every j is from 1 to r, so we are putting the value of the j and we see what happened. Eta 1 it is equals to summation k is running from 1 to n xi k into tau 1k. I am writing here like this. Eta 1 it is equals to, now summation over k is from 1 to n, therefore xi 1 tau 1 1 plus xi 2 tau 1 2 up to so n plus xi n tau 1, sorry, not tau n 1, sorry, not tau n1, this is tau, j is, the value of j is 1 and therefore tau 1 n. Now for j equals to 2, here we have eta 2, here we have eta 2, that means the value of j it is equals to 2. Again here the summation is from k to n, therefore here the first value of k is xi 1 tau 2 1 plus xi 2 tau 2 2 up to so n plus, here we have xi n into tau 2n. This is continue up to the value, last value of j is r. That means here we are putting j equals to r. We get here eta r, it is equals to xi 1 tau r1 plus xi 2 tau r2 up to so n plus xi n tau rn. In this way, this equation 4, we simplify this equation 4 in this way. Now here we observe that we can write all this equation in terms of the matrix like this. Here we are taking in the column vectors eta 1, eta 2 up to so n eta r. It is equals to, now we are taking tau 1 1, tau 1 2 up to so n tau 1 n. Here tau 2 1, tau 2 2 up to so n, here tau 2 n up to so n, here tau r1 tau r2 up to so n tau rn into another column vector is xi 1, xi 2 up to so n xi n. Now here we write down all these equations in terms of the matrix form like this. Here in matrix multiplication we can say that here eta 1 it is equals to tau 1 1 into xi 1 plus tau 1 2 into xi 2 plus up to so n tau 1 n into xi n. That is our first equation. Now eta 2 that is equals to tau that is equals to tau 2 2 into xi 1 plus tau 2 2 into xi 2 up to so n plus tau 2 n into xi n. That is our equation second. In the same way eta r that is equals to tau r1 into xi 1 plus tau r2 into xi 2 up to so n plus tau rn plus plus tau rn into xi n. That means the last equation. In this way these equations can be expressed in terms of the matrix, and therefore now we write down all this in the terms of matrix like this. Here we take TEB. Here we take TEB. Here E is the set of it is the basis for capital X and B is the basis for capital Y, and TEB it is equals to the matrix tau JK. Tau JK, it is the matrix tau JK, like this here, where E is the basis for capital X and B is the basis for capital Y. And here we are writing Y tilde. Y tilde, it is equals to the sequence eta j. It is nothing but a column vector. And X tilde, it is equals to the sequence, it is equals to the X tilde, it is the psi k. It is again a column vector, and then this equation is written in the form of Y tilde, it is equals to TEB into X tilde. In this way, the equation 4, that is eta j equals to the summation over k is from 1 to n tau jk into psi k for all j equals to 1 to up to so and r. This equation, we write down this equation in terms of matrix and giving the column vectors as y tilde equals to eta j, x tilde equals to psi k, and the matrix TEB is equals to the matrix tau jk. We get the equation y tilde it is equals to TEB into x tilde, where y tilde it is again a column vector eta j, x tilde it is equals to the column vector psi k, and it is the matrix. That means here, if a basis capital E for capital X and a basis capital B for capital Y are given with the elements of E and B arranged in some definite order, that is very required condition for this, that the elements of capital E and capital B are arranged in some definite order which is arbitrary but fixed. Then the matrix TEB is uniquely determined by the operator, by the linear operator T, because here we are getting this matrix with the help of the linear operator T, and that linear operator T, because here T is the mapping which is from X to Y, and here we starting with the small x with the element of capital X, and with the help of this small x we are getting here the Tx, that is the image of the point, image of the vector x, that is Tx, and then as x is finite dimensional, therefore it has a basis, as y is also finite dimensional, therefore it has also the basis, and then using the equation that is y equals to Tx, we get the matrix that is TEB. That means with the help of this linear operator we obtain a matrix where the basis for capital X and capital Y are given, and the elements of E and B must be arranged in some definite order. In this way we say that the matrix is uniquely determined by the linear operator capital T. That means we say that the matrix TEB represent the operator capital T with respect to those bases. In this way we see the point linear operators on finite dimensional spaces. Here again one point is that as we writing here y tilde it is equals to TEB into x tilde. Similarly the equation thrice B. The equation thrice B is that TEK that is equals to the summation j is from 1 to r tau jk into br. Tau not br, that is the bj. Tau jk into bj. This is true for each k. For all k, that is equals to 1 to up to so and n. That means here we say that TEK that is equals to the summation j is from 1 to r tau jk bj, and here this equation can be written in matrix notation in the same way as we take, that means the equation like this, eta j equals to the summation over k, which is from 1 to n tau jk xi k, tau jk xi k. This equation is written in terms of the matrix format y tilde equals to TEB into x tilde. In the same way, the equation TEK, that is equals to the summation over j is from 1 to r tau jk bj. This equation can also be written in the matrix form as TE, it is equals to TEB transpose B. Here TE, it is the column vector with components TEK. TE is a column vectors with component TEK. That means here we have the components TE1, TE2 up to TEN. In the same way, B is also the column vector with the components Bj. It is equals to B1, B2 up to Br. And here we write down this transpose, that is the transpose TEB. TEB transpose is the transpose of the matrix TEB, and we write down this transpose because in thrice B the sum is taken over J. That is our equation thrice B. This is the equation thrice B, and in this equation we take the sum over J, and in this equation we take the sum over K, and therefore as here we are taking the sum over K, and therefore here we have the equation y tilde, that is equals to the matrix TEB into x tilde. But here in the equation thrice B, the summation is taken over J, and due to this, here this equation is written in the form of TE. It is equals to TEB transpose into B. In this way, we say that the linear operator represents the matrix. In the same way as we see the examples of the linear operator, in that examples we show that matrix is a linear operator. From this example, we say that matrix represent the linear operator, and therefore on a finite dimensional vector space, a linear operator T determines a unique matrix, and conversely any matrix determines a linear operator. And in this way we see the first part of the topic, that linear operators on a finite dimensional spaces. In the second part we see linear functionals on finite dimensional spaces. So we start with the finite dimensional vector space. Here let capital X be a finite dimensional vector space. As capital X is finite dimensional vector space, that means the dimension of X, that is equals to n, which is strictly less than infinity, and therefore small x has a basis E1, E2 up to En is a basis for capital X. As it is a basis for capital X, that means every element of capital X has a unique representation in terms of E1, E2 up to En. Now here we consider f be a linear functional on X. That means f is a mapping which is from X to K, where K is a scalar field of X, and f is here, we consider f as a linear functional on X. As it is a linear functional on X, and we know the algebraic dual space X star. Algebraic dual space X star be the set of all such linear functional. That means X star be the set of all f such that f be a linear functional on capital X. It is a linear functional, and therefore for any f belongs to x star and for every x belongs to capital X, we have here, as x is the element of capital X, therefore x is has a unique representation as x is equals to, we are writing here, xi1 e1 plus xi2 e2 up to so n plus xin en. That is x, it is equals to summation over j is from 1 to n xi j e j. And as f is a linear functional on capital X, therefore f is applying on this x, and therefore here we have f of x, it is equals to the f of this summation j is from 1 to n xi j e j, and that is equals to, because f is linear and therefore it is equals to summation j is from 1 to n, xi j is a scalar, therefore xi j into f of e j. Now we are putting f of e j is equals to alpha j, that means it is equals to the summation j is from 1 to n xi j into alpha j, where alpha j it is equals to f of e j. Now we give it the equation number 1, where alpha j it is equals to f of e j for each j 1 less than or equals to j less than or equals to n. From this here we say that f is uniquely determined by its values alpha j, because here this is f of x is written in terms of alpha j, and therefore we say that because xi j is a coefficient of alpha j, that is nothing but the coefficient of this e1 e2 and so on, therefore here we say that f is uniquely determined by its values alpha j at the n basis vectors of capital X. In the same way here we have for each j alpha j equals to f of e j, that means every n tuples of scalars alpha 1 alpha 2 up to so n alpha n determines a linear functional on capital X, and therefore here we are getting that linear functional on a finite dimensional spaces is uniquely determined by its values alpha j, and every n tuples of scalars determines linear functionals on capital. We consider n tuples. We consider the n tuples 1, 0, 0, 0. Second is 0, 1, 0, 0. Third is 0, 0, 1, all are 0. Continue this up to 0, 0, 0, and the last is 1. We have that f of x equals to, here we get summation j is from 1 to n xi j into alpha j, where each alpha j it is equals to f of e j for each j. Therefore from this equation here we observe the n functionals, and we denote it by f1 f2 up to so n fn with the values. Here we have the values. By using this here we say that fk of ej that is equals to delta jk, and it is equals to 0 if j not equals to k, and it is equals to 1 if j equals to k. It is called as a Kronecker delta, because here the f1 it is a linear functional. We are getting the linear functional like this. f1 gives the value 1 at the first place and all remaining are 0. f2 we get this linear functional as f2 of ej, that is equals to delta j2, okay, and it gives the value 1 at the second place, and for the remaining places it is equals to 0. In the same way we get the functionals f1 f2 up to so and fn. In this way and here this delta jk it is called as a Kronecker delta.